but I do appreciate it. I appreciate you humoring me. All right, so let's look at these stars. We went from being able to see a few hundred of them with our light-polluted skies to now well over 3,000 just by turning off all the lights. There's something new that wasn't there a moment ago, and that's some light here, this streak of light going across our sky. Does anybody know what that is?
No.
A shooting star.
Yeah, excellent. I heard a bunch of people say it. That is the Milky Way. That's our galaxy. So let's talk about it. As it turns out, every single star you see in the sky is a part of the Milky Way galaxy, including our own. I can point out a random star over here, here, it doesn't matter. They're all within our galaxy. And the reason I can so confidently tell you that is because of how far away things are in space. We can see other galaxies, depending on the right time of year, if it's dark enough, if it's clear. But we can't see the individual stars within them. Our eyes can't resolve something that dim, that far away. So when you see a star, it's relatively close to home. It's in our galaxy. But that's absolutely correct. We call this our galaxy. Really what this is the center of the Milky Way. And all of this light is just a very large accumulation of stars and gas and dust that we look at when we look towards the center of the galaxy. All right, well, let's get ourselves oriented so we know exactly which way we're looking here. So what I've just pulled up now is what we call our cardinal points, our north, south, east, and west. And all the seats here in our theater face south, all right? Which means this is east over here on our left, west over here on our right, and of course north behind us. And the reason I pull these up is because when you're stargazing, especially if this is something new to you that you're not used to doing often, it's very, very easy to get disoriented with where you're looking in the night sky. So let's talk about motions of objects for just a minute here. We may already be familiar. Well, let me ask you, there's a lot of kids in the audience tonight. So this question's for the kids. What direction does the sun rise every day?
East. North. North.
All right, well, I heard all four. So
North.
This has got to be right. It is the east, okay? Which means, boys and girls, what direction does it
You
set?
said west.
West. Okay, well, here's a question for everybody. It's a little more complicated.
west.
At noon every day, the sun is in a particular position in the sky.
See.
What direction is it?
South.
It is south. Yes, very good. So what that tells us is the path of the sun rises in the east, it goes like this, across our southern sky, and then it sets in the west. Now, it's nighttime. Why are we talking about the sun? Well, because it's not actually the sun moving across our sky, right? It's the earth rotating. So this is the path, this is what we see, Earth's rotation. So not only is the sun going to rise and set in the east and in the west, so are the stars. And we're going to see the stars move across our southern sky and then set in the west. So let's talk about a couple of these things. Actually, I want to first, before we talk about stars, talk about planets. There's actually a couple of planets in our sky right now. You guys may have heard of this whole planetary parade thing that they've been talking about for a while. It's nonsense. I'll break it to you. It's nonsense. Listen, I'm never going to complain when astronomy gets talked about, when it's in the news and on social media, but it's nonsense. The planets are always in a line. Always. Let's talk about it. In the sky right now for us to see, there are two planets. Okay? Now, not all the planets we can see with the naked eye. Right? Neptune and Uranus are just not there. We need a telescope.
Too far.
But there's two you could see right now by just looking at the sky. I want you guys to try to pick.
Mars.
Well, okay, so Mars is one of them, yes. The other is Jupiter.
Venus.
Yes. But what I meant is, I want you guys to pick a star in the sky that you think might not be a star, might be a planet.
Venus.
All right, I'll give you a hint. It's not this one right here.
That's the moon.
That's the moon, okay? Yes, the one right next to it, yes. That is Mars, very good.
Yes.
The other one,
It's right. Wait.
not this one,
I see it. No.
right here.
Yeah.
That's Jupiter. All right, let's take a closer look. I want to take a closer look at Jupiter. So let's zoom in. Because, guys, this is what we're going to be looking at through the telescope after the show.
Woo. Yes.
Now, when we look at Jupiter, even through a telescope, we can see these features here. We can see these bands going across its atmosphere. And we can see these spots, these little swirls
Oh, I know.
all over, including this one here.
Uh-huh.
Anyone know its name?
The red
Pretty much.
dot.
Yeah, we got there. It's called the Great Red Spot.
Oh, I
All
forgot.
right? The Great Red Spot.
The great
I'm going to tell you guys a quick little story here. Astronomers are not really creative when naming things. All right? It's called the Great Red Spot because that's what it is. The story I have for you is there's a telescope in South America, in Chile, up in the Andes Mountains, really far away from light pollution, right? It's a great place for astronomers to study the southern sky, and we do this, make these observations, learn a lot about the universe. When it came time to name this observatory, this telescope, the official name they settled on is the Very Large Telescope. All right? I'm not making that up. Okay. There was another one that was proposed, but it ended up being canceled, called the Overwhelmingly Large Telescope. All right. So there's not a lot of creativity that goes into these naming schemes here. So that's what it is. It's the Great Red Spot. But more specifically, what is it? It's a hurricane. It's a storm.
Yeah.
With wind speeds unlike we've ever seen here on Earth, over 400 miles an hour.
Wow.
That's like roughly the speed of sound.
Wow.
Okay. Now, what's more impressive is its size and its age. This is a very old storm. We first observed this over 250 years ago.
Wow.
It was probably there for much longer, but that's when we first saw it with a telescope. It's still there. Now, it's getting smaller, so it will most likely dissipate within the next few hundred years. But it's a very old storm. But the size is really what is the claim to fame for this spot. Now, when we're looking up into space, it's one of the hardest things, well, I should say one of the hardest things for us to grasp is this idea, this concept of spatial thinking. And what that means is understanding the scale and magnitude of things. We are very accustomed to a certain set of things here on Earth. We know how long a day is. We know the lifespan of a person. We know how long it takes to get to school, get to work, whatever that may be. When we're looking up into space, throw that all out the window. Right? We are talking about magnitudes that we can't even comprehend sometimes.
Light years.
So what I like to do is try to give folks a sense of scale. And one of the great ways to do that is to look at Jupiter. I can make Jupiter as big as small as we want. That doesn't actually give us a good representation of its size. But what if I put something next to it that we're a little bit more familiar with? So what I'm going to do is put Earth next to the Great Red Spot of Jupiter. Our entire planet. It looks like this. And so this is this little guy right here. You can easily fit 2 of our entire planet in this spot on Jupiter. Now imagine, or really think, look how big Jupiter is when we make that comparison. I want to do a quick thought experiment with you guys here. If I were to ask you, and you don't have to shout anything out for this, just think about it. If I were to ask you, if we took every object in the solar system, the sun, the 8 planets, the minor planets, the asteroids, the comets, the hundreds of moons, and we put it all on a scale, okay, out of 100%, what percentage do you think the sun would account for? That's my, just think about it. What percentage do you think the sun would account for? 30%, 50%, more than that? The mass of the sun, compared to the mass of the entire solar system, is 99.85%.
Wow. I was thinking of 90.
That is a margin of error from just saying 100%. Jupiter accounts for 0.14%. So basically everything else. Everything besides Jupiter and the sun, Earth, the other planets, the moons, all that other stuff, accounts for 0.01% of the mass of the solar system. That is how incredibly massive Jupiter is, but really that is how incredibly massive the sun is. All right, so there's a bit of scale for us. Now, Jupiter has dozens and dozens of moons. There are 4 that we have known about for hundreds of years, since the 1600s. They were first discovered by the astronomer Galileo Galilei back in, I think it was the first decade of the 1600s, and we aptly call them the Galilean moons because of this. Now, he looked at them through a telescope, and he saw these 4 little dots. Now, he did not see them how I'm about to show you, but he just saw them, they looked like stars, okay, but they were moons. This is what they look like. The Galilean moons.
Wow.
The one all the way on the left is called Io. It is the most volcanically active object in our solar system. There are more volcanoes on this moon than there are on Earth, or even on Venus, the most volcanically active planet. Europa here is, in my personal opinion, the crown jewel of our solar system. We have detected oceans of liquid water on this moon using thermal scanners. Liquid water. Let's talk about that for a second. The mantra of NASA since pretty much forever has been follow the water. On Earth, where there is water, there is life. And that's going to make the most sense for us. We're trying to find life elsewhere in the universe. Look at where the water is. And there is plenty of it on this moon here. Plenty of it. We actually just launched a mission called the Europa Clipper, which I think it's going to get to this moon within the next 5 or 6 years. It takes a long time to get to Jupiter. But we're going to try to see what's underneath the surface of ice that we can look at here. And see if we can answer that question. Is there life elsewhere in the solar system?
No.
Ganymede, largest moon in the solar system, bigger than the planet Mercury. But it's not a planet itself because it's orbiting Jupiter. Callisto, just this past week, I read a paper that was published indicating that we now have evidence that this moon also has liquid water underneath its surface too. So that might be an area of future study as well. So Jupiter's moons are fascinating. And guess what, guys? If you look through the telescope with me this evening, you can see all 4 of these. They're out.
Really?
They, again, are just going to look like little dots. But if you've never done this before, you'll be able to see moons from another planet for the first time ever. All right. Now, I want to very briefly talk about this planet parade thing that's been going on. And I want to show you why I said a few minutes ago that it's kind of a bunch of nonsense. So, in order to explain this, we need to look at our solar system from the outside. Okay? Right now, we're on Earth, which is great because now we can see the stars. But if we were to go out into space, we would see the solar system a little bit different. Let's see. This model of the solar system we call an orrery. Okay, it's a scale model. It's not scaled to size or distance, but it's showing us the order of the planets and the general shape of our solar system. When we look at this orrery, we're looking at it from the top. Okay, and we see the sun in the middle, and the inner planets are very close. Then Jupiter, Saturn, Uranus, and Neptune. But here's the thing. If we were to look at this from the side, something really interesting happens. Take a look at that. All the planets lie on this plane here. Our solar system is flat. It's actually flat. Which is kind of funny to think about, because there are some folks that think the Earth is flat, but the solar system actually is flat. And as it turns out, large-scale objects tend to be relatively flat. The Milky Way is as well. Now, this isn't a crazy thought once you actually break it down. In physics, we have something called the conservation of angular momentum. You may have heard of this before in terms of looking at a ballerina or an ice skater spinning around, right? And when they pull their arms to the center, they start to spin faster and faster. Right? Well, this happened early on in our solar system while it was being formed. Stars form in large gas clouds that we call nebulas, and our solar system is no different. So the sun formed in the middle, and as the gas started to pour into the center due to the sun's gravity, well, it started to rotate very fast, just like the ballerina or the figure skater does with their arms. As that happens, it rotates really quickly, it flattens out. So it's actually not a surprise at all that our solar system is shaped like this. Now, what does that mean for this whole planetary parade thing? Well, from Earth, right, back here on Earth, if we were to look at this line of planets across the sky, it would look like this here. Okay? This is called the ecliptic. And by definition, the ecliptic is not only all of the path of all the planets, but also the sun, because it's all on the same plane. So the ecliptic is realistically a calendar. What this is really showing us is where the sun is throughout the year. So here's the middle of July, and it's showing the sun is here, right? Now, of course, we can't see that now because it's still winter time, so it makes sense that our nighttime sky in the winter would be our daytime sky in the summer. But notice, here's Mars right on this line.
Are you kicking the seat?
All the planets always lie along this line. Okay? So when people were saying, oh yeah, the planets are all in a line, that was my response. They're always in a line.
Somebody needs to stop kicking the seat.
Now, it was nice that they were all out in the sky at once, but again, when I mentioned Uranus and Neptune, I said you can't even see those without a telescope to begin with. So that was the whole deal with the planetary parade situation. Now you know. All right, let's talk about some stars now. Enough of these planets. So, we're going to talk about the stars from two different perspectives. I'm going to give you a little history from a human perspective, what I call the anthropology side of things. And then we'll talk about the science side of things. So, humans have been looking up at the night sky for millennia, since we were able to, for thousands and thousands of years. And long before the internet, television, even long before books and written words, we had the stars. And people forever have been looking at these stars and telling stories with them. If you put yourself in the mind of someone 10,000 years ago, sitting around a campfire, looking up at the night sky, and maybe listening to someone talk about different heroes, different gods and goddesses, mythical creatures and beasts, all while using the different shapes that we make with the night sky. Now, the beauty of this is a lot of these shapes and stories have survived the test of time, and we can still see and we still know of these stories from thousands of years ago. Now, we call these constellations. Now, everywhere on Earth you would go, there's always going to be different stories and different shapes, different constellations. Now, here in the 21st century, we have a catalog of 88 constellations that we officially recognize. Here's what they look like.
One looks
And it's
like
about
a
half
stick
of them.
man.
The other half we can't see because it's nighttime, and or they're out when it's daytime, right? So we won't be able to see them. But these are some of the constellations. And again, this changes with the seasons as well. So that's the winter sky, what we're looking at. But if you come back in the spring, in the summer, it'll be completely different. One of these very famous constellations and stories is our buddy Orion, right over here. The Mighty Hunter. Now, he is usually one of the first objects that people learn when they're trying to look at the night sky. We can see his two shoulders, these two stars, Betelgeuse and Bellatrix. We have his belt here, with 3 stars going across. And we have these 2 stars, Rigel and Saiph, that are his legs or his knees. That's Orion. Now, inside of this constellation, what we'd call his sword, right underneath the belt here. If you look, there's kind of like a little cloudiness to it. You know, let me turn off the trace here a little better. I'm going to give you guys a little trick to looking at dim objects in the sky. Don't look directly at it. I want you to see what's going on right here, so I want you to look here. Okay? If you look here, you will be able to see what's over here clearly. It sounds counterintuitive, but the reason for this is because the light receptors in our eyes are actually more sensitive on the sides than they are looking forward. So you can see dimmer objects if you avert your vision a little bit. So that little cloudy area, you can see with the naked eye. You can see it tonight when you look up at the sky. That is a nebula. That is the Great Orion Nebula. And that's one of the things I'd like to look at through our telescope if we have some time after Jupiter. That is a star-forming region. So that's where new stars are being created. It is a large cloud of gas and dust. So, that's Orion. I want to point out a couple other constellations, too. Let me get Orion back up here. Now, Orion is always followed by his pair of hunting dogs, which are 2 constellations that we call Canis Major and Canis Minor. And they are to the east of him, right? They're behind him. How we find it, well, just look to the southeast of Orion, and you'll see this really bright star here. This star is actually the brightest star in the night sky. Does anybody know what we call that star? Okay, I'm hearing a whole bunch of different things. We call this star Sirius. Yeah, Sirius. Yes. If anyone was saying the North Star is actually very dim. Right? We can see it, but it's not the brightest star in the sky by any means. It just happens to be always pointing north. Right? It happens to be lies where our north celestial pole is. But this is Sirius. This is the dog star, and that's how we find the constellation Canis Major. Looks like this. There's our picture of it, a little bit more flattering.
Good boy.
Now he's got another one, the puppy, the little dog, Canis Minor. To find that, we're going to look at Betelgeuse and go directly to the east until we come across this star here. This star is called Procyon, and Procyon is the bright star of Canis Minor. Let's see what that looks like. Isn't that so cute? Just a line, yeah. Here's our picture. Ancient peoples had much better imaginations than we do. I will say that for sure. But there's the family. Now, they're often depicted fighting some of the other objects in the sky, like a constellation that's directly in front of Orion. This guy here. This is called Taurus, the bull.
Taurus.
And we see Orion and his dogs are going head to head in the night sky with this constellation. We see the bright star here. This is called Aldebaran. That's the eye of the bull. And this is where Jupiter is right now. Jupiter, because of how far away it is from the sun, takes about 12 years to orbit, meaning it stays in this constellation for a while. You know, in a year from now, it might be over here, but you're going to see it in this area for quite some time. Now, the moon, on the other hand, which we haven't really talked about tonight, because the moon orbits the Earth once every month, roughly, right, every 29 and a half days, it's going to move a lot quicker. So tonight, the moon and Mars are really close. But if you look at the night sky tomorrow, the moon's going to be like over here. And the next day, over here. Right, so the moon moves very quickly throughout the sky because, you know, it needs in 30 days to do a full 360 degrees around the Earth. All right. So that's some constellations. Now, we could spend hours talking about the stars themselves, but let's move on to something else. Now, I need to give you guys a little introduction to how light works. So we're going to talk about that for a couple of minutes. And the reason we're going to talk about this is because this is how we observe the universe, right? If we're going to talk about what the stars actually are, we're looking at the light from them. Astronomers can't go to the stars, not yet at least. And we have to make all our observations and our understandings from right here on Earth. So, when we look at the light from the stars, we are talking about this here. This is called the electromagnetic spectrum. This is all the different types of light. Now, for our purposes, light travels in waves, like sound, but much, much faster. So, we see these waves here. Now, notice that the ones over here are much more bunched up. They're closer together, and the ones over here are much more spread out. We call this distance the wavelength, right? The distance between the waves. This is what's going to determine the type of light we are observing. Everything you see up here is light. But guess what, guys? The only thing we can see with our eyes is this tiny little bit in the middle here. This is called the visible light. Everything else is invisible to us. Just because it's invisible, though, doesn't mean we can't use it, and we do. Radio waves we use constantly. This is what powers our internet. Our phones glow in the radio wave, but we can't see it. It's invisible to us. Microwaves we use to heat up our food, right? We're using light waves that are invisible to our eyes to heat up the food. Infrared is heat, right? The heat that our bodies give off, the heat that planets give off, and so on and so forth across the spectrum. All of these types of light are used by us, but all we can see is visible light. So if we study the light from the stars, we can actually learn a lot about it. If you look at starlight through a prism, right, through something that refracts the light, we can study something we call spectroscopy. We can learn what stars are made of through this process. We can learn about their temperatures, right? Their thermal radiation. We can learn about their motion, how they're moving in space, all by studying these stars. And what we've learned is pretty interesting. We've learned that, well, when we ask the question, what is a star? This is what stars are. Stars are made of hydrogen and helium, the two most basic elements in the universe. Right? The element number 1 and 2 on the periodic table. Inside the star, deep within its core, there is a nuclear reaction going on. It's called fusion. Now, this is the opposite of what we might be more familiar with, which is nuclear fission. Fission is splitting an atom. That's like the atomic bombs, nuclear power plants. That's like radioactive decay, right? It's splitting the atoms. This is the opposite. This is combining the atoms together. Hydrogen, through a couple of steps, will combine together to form helium, and so on and so forth down the periodic table. That's what's going on in stars, just like our sun. Now, as a byproduct of this, an immense amount of energy is released. Energy in the form of visible light, of heat, right, of all these different wavelengths that we can observe. That's why the stars glow. That's why the stars glow. So, what I want to do is take you guys on a scaled view of our observable universe. We're going to take some stops along the way, and I'll talk a little bit more about this whole idea of light when we get to the right spots. But I really want to give you guys this sense of scale here. All right? So let's do that. Let's take a look at Earth first. And what we're going to do is we're going to launch off of Earth. Actually, you should see Earth rising up in just a moment.
There you go.
There it is. All right. So this is Earth this is showing us the light pollution, right? So here's New York, here's Long Island. Look at all that light. But we're gonna go ahead and put all the light on Earth to make it daytime. And the first stop on our journey here is a distance from Earth of about 250,000 miles away. This is the distance from Earth to the Moon. 12 human beings have stood on the Moon's surface. Those were the Apollo astronauts in the late 60s and early 70s. And we haven't gone back since. Now, NASA's working on the Artemis missions. As long as those are still able to go through, we will be going to the Moon again sometime soon. And this is the view that those astronauts get. Earth on this very small ball in the background. All right, let's talk about the speed of light. When we measure things in space, as I said to you guys earlier, we need to change our sense of scale here. So we're not going to use inches or feet or miles. It's not enough. We're going to use light, because light is the fastest thing in the universe. So the speed of light in space is about 300 million meters per second. 300 million meters every single second. That's how far light travels, or how fast light travels. So what we've done is we said, okay, let's measure this distance over the course of a year, and we'll call that a light year. That's what the term a light year is. It's about 6 trillion miles of space. This sphere here represents 200 light years of space. This is called the radiosphere, and it's showing how far our radio transmissions have reached in outer space. And remember, radio is light, so it's traveling at the speed of light. Now, we've been doing this for about 100 years, so 100 years in all directions would make this 200 light years wide.
It feels like we're moving back.
Let's take a look at the Milky Way. All right, so here's our galaxy. Now, this is where we just came from. And remember, guys, that's 200 light years of space, with 1 light year being 6 trillion miles. If we were to measure our galaxy from edge to edge in terms of light, it's a little over 100,000 light years across. Right, that's 100,000 times 6 trillion miles. That's how large our galaxy is. Even at the speed of light, it takes time for things to go across space. For example, the light that's leaving these stars here will travel across the galaxy for 100,000 years before it reaches over here. When you are looking up into space, especially deep space, you are literally looking back in time. Let me explain. The center of our galaxy is about 27,000 light years away. If you're ever able to see that on a really nice night, really dark, no light pollution, that streak across the sky that we talked about, that's looking at light that has been traveling across space for 27,000 years. You're looking at what that area of the sky looked like 27,000 years ago. Now, it probably hasn't changed all that much in the past 27,000 years, but we will not know that for another 27,000 years. That is how slow light really is when we're looking up into space. Now, I'm going to bring us to the side of our galaxy so we can now see what I mean here about this whole rotating disks, conservation of angular momentum. And we're going to see that the galaxy, like our solar system, is relatively flat. This is the view we get. This is why it looks like a streak of light going across the sky when we can see it. Even though it's 100,000 light years across, it's only a dozen or so light years thick at the largest part of the central bulge here. So that's our galaxy. Now, it's incredibly difficult for us to see through this. Okay? And I'll explain what that means, what the implications of that are in just a moment. Now, at this level, all we are able to see is other galaxies. Each one of these little dots is not a star. It's a collection of stars. Our galaxy